In the last class, we have studied about some important theorems which are related to the real numbers. So, which were those theorems? If p is a prime number and if p divides a square, then p certainly divides a, where a is any positive integer. Also, in the last class, we had proved that root 2 is an irrational number. Now, today in this class, we will be studying about the terminating and the non-terminating decimal expansion of rational as well as irrational numbers. So, in the 9th class, we have studied about rational numbers as well as irrational numbers. So, what are rational numbers? Rational numbers are nothing but those numbers which can be expressed in the form of p by q, where q is not equal to 0 and p and q are integers. And similarly, what are irrational numbers? Those numbers which cannot be expressed in the form of p by q, where q is not equal to 0 and p and q are integers. So, which are expressed in the form of p by q are rational numbers, and which are not expressed in the form of p by q are irrational numbers. Now, let us study about their decimal expansion. So, a rational number has a terminating decimal expansion. So, what do you mean by the word terminate? Terminate means to end, right? I think you have all played PUBG, right? So if you fail to complete the task, it shows that the mission is terminated. So it means the mission has ended. Similarly, a rational number has a terminating decimal expansion. So consider an example: 7 divided by 8. So if 7 is divided by 8, the long division process ends after a certain point. Then we call such type of division or such type of numbers as rational number. In rational numbers, the decimal expansion or the remainder of the particular dividend becomes 0. The remainder becomes 0, as well as the quotient ends after a finite number of steps. In rational numbers, the first point is the remainder becomes 0, as well as the quotient ends after a finite number of steps. For example, consider 7 divided by 8. So 7 is divided by 8. So 7 is a smaller number, so it cannot be divided by 8. Hence, we take a decimal point, 0 point. So then we take a 0. 8 is a 64. Remaining is 6. Then again we take a 0. 8 7 is 56. Remaining is 4. Again we take a 0 and 8 5 is 40, which is equal to 0. So this is an example for terminating decimal expansion, and this is also an example for rational numbers. So the remainder becomes 0. Here we have the remainder is 0, right? And the quotient ends after a finite number of steps. The quotient has ended here. It is not continuing, right? Hence we take this as the terminating decimal expansion, and this is only meant for rational numbers. Coming back to non-terminating decimal expansion. So terminating decimal expansion, its opposite is non-terminating. Here the remainder becomes 0, here the remainder never becomes 0. Here the quotient ends after a finite number of steps, and here the quotient does not end. It keeps on repeating after a point. Consider an example: 1 divided by 3. 10 divided by 3. When 3 is divided by 1, 10 is divided by 3, we get the quotient as 3.333 and so on. It keeps on repeating, or else it keeps on recurring. So this type of numbers where the remainder never becomes 0, as well as the quotient keeps on recurring or repeating, those types of decimal expansion are called as non-terminating decimal expansion. And these non-terminating decimal expansion is only meant for irrational numbers. So terminating decimal expansion is meant for rational numbers, and non-terminating decimal expansion is meant for irrational numbers. So I hope up to here it is clear. Now here we have only small numbers: 7 divided by 8, 10 divided by 3. We can do long division and we can classify them as rational and irrational. Suppose they have given you an example like something like 15 divided by 80,000 or else 3 divided by 1 lakh. Are you able to do it by long division method? No, right? It takes years together, not days. It takes years together to classify it as terminating or non-terminating. Hence, we have improvised this technique to a further level in which we are going to study now. Now that we have studied about what are rational numbers, what are irrational numbers and their decimal expansion, that is terminating as well as non-terminating decimal expansion, let us study how to deal with numbers when they are high, when they are relatively high. Consider an example 0.375. 0.375 can also be written as, in the P by Q form, it can be also written as 375 divided by 1000. In 9th standard, you have learned how to convert it into a P by Q form. 375 divided by 1000. Now, 375 divided by this 1000 can be also be written as 10 raised to 3. 10 raised to 3 is nothing but 10 into 10 into 10, which is nothing but 1000. So, 375 divided by 10 raised to 3. Now, we shall, to simplify this a little more, we shall prime factorize 375. So, the prime factorization of 375 is 3 into 5 cube. Okay? And we can write this term as 2 into 5, 2 into 5. The prime, since we have prime factorized the numerator, we should compulsorily prime factorize the denominator as well. So, the prime factorization of 375 is 3 into 5 cube. And the prime factorization of 10 is 2 into 5 whole raised to cube. Since it is 10 cube, it can also be written as 2 into 5 whole cube. Now, 3 into 5 whole cube is equals to, according to the law of indices, a into b raised to m is equals to a raised to m into b raised to m. A into b raised to m is equals to a raised to m into b raised to m. Now, 5 raised to 3 and 5 raised to 3 gets cancelled. Now we are left with 3 divided by 2 raised to 3. Okay? Up to here, I guess you have understood. Similarly, consider the example 0.104. Now it can also be written in the P by Q form as 104 divided by 1000. Similarly, 104 divided by, this can be written as 104 divided by 1000. Now the prime factorization. Now we shall again prime factorize as we did in the earlier problem. Prime factorize 104 and prime factorize 1000. Prime factorization of 104 is 13 into 2 raised to 3. 13 into 2 raised to 3. And the prime factorization of 10 is similarly as 2 into 5 raised to 3. Again, 13 into 2 raised to 3, a into b raised to m is equal, a into b raised to m is equals to a raised to m into b raised to m. Therefore, 13 into 2 raised to 3 divided by 2 raised to 3 into 5 raised to 3. So, 2 raised to 3 and 2 raised to 3 gets cancelled. Now, we are left with 13 divided by 5 raised to 3. Again, consider a third example 0.0875. Now, it can also be written in the P by Q form as 875 divided by 10,000. Now, 875 divided by 10,000 can also be written as 10 raised to 4. Now, prime factorize the numerator as well as the denominator. The prime factorization of 875 is 5 cube into 7 divided by 10 raised to 4 is 2 into 5 whole raised to 4. So, 5 cube into 7 divided by 2 raised to 4 into 5 raised to 4. Now, 5 raised to 3 and 5 raised to 4. Here we are left with 5 raised to 1. Here we have 5 4 times and here we have 5 3 times. So 3 times here and 3 times here gets cancelled and still we are left with 1 5 in the denominator. As numerator as it is 7 divided by 2 raised to 4 into 5 raised to 1. Now we observe a pattern here. The denominator of this particular example is 2 raised to 3 and this particular example is 5 raised to 3 and this particular example contains both the terms 2 as well as 5 raised to 3. So, observe the first example, the denominator is 2 raised to something, 2 raised to something. And in the second example, the denominator is 5 raised to something. In the third example, we have 2 raised to something into 5 raised to something. So, here you have to concentrate. 100%. Okay. If we have to find a rational number or not, we need to first prime factorize the denominator. We need to prime factorize the denominator first. And if and only if the prime factorization of the denominator comes as 2 into some power n, say n, 2 into some power n and 5 into some power m, 2 into some power n and 5 into some power m. If the denominator comes in terms of 2 raised to m into 5 raised to m, then we conclude that it is a rational number. If it does not comes in the form of 2 raised to m into 5 raised to m, then we conclude that it is not a rational number. Okay, are we clear with this? I will explain once again. So, if in the denominator, if a particular number is given 5 divided by 5 lakh, the denominator is 5 lakh. Now, if the denominator 1 prime factorized, if we get in the powers of 2 raised to n into 5 raised to m, okay, 2 raised to n into 5 raised to m, then we are 100% sure that it is a rational number. If not, it is not a rational number, it is an irrational number. I hope this session is clear. Okay, now we shall solve some examples relating how to classify the given set of numbers as rational and irrational based on 2 raised to n into 5 raised to m. Okay, now that we have known how to classify a rational number as well as an irrational number depending upon the denominator of the given fraction. Now we shall study an important theorem which will be very helpful in our next upcoming problems. Suppose let x be a rational number whose decimal expansion terminates. Suppose we know that they have given a fraction whose decimal expansion, when we do by long division method, it terminates. Then x can be expressed in the form of p by q, where p and q are co-primes, and the prime factorization of q is of the form 2 raised to m into 5 raised to m, where n and m are non-negative integers. So, the explanation of this theorem is like this. So, suppose you are given a fraction and by long division method you have come to a conclusion that it terminates. It is a terminating decimal expansion. Now, that particular fraction can be expressed in the form of p by q, where the prime factorization of q is in the form of 2 raised to n into 5 raised to m. So, this was about theorem 1. Okay, I hope it is clear. And most important point, that is n and m are non-negative integers. So, it should not be a 2 raised to minus 1, 5 raised to minus 3, it should not be it should not be negative integers. It should compulsorily be positive integers. So, what is the converse of theorem 1? Suppose, let x is equal to p by q is a rational number such that the prime factorization of q is of the form 2 raised to n into 5 raised to m, then x has a decimal expansion which terminates. So, from the theorem 1 we know that we are given a fraction, by long division method we come to a conclusion that it terminates, and hence that particular fraction can be expressed in the form of p by q, where the prime factorization of q is expressed in the form of 2 raised to n into 5 raised to m. Similarly, converse tells that if x is equal to p by q is a rational number, suppose they are given a fraction 1 by 2, okay? It is a rational number and it can be expressed in the denominator, that is 2. If we consider the example 1 by 2, the denominator is 2. And 2 can be expressed in the form of 2 raised to n into 5 raised to m. Then that particular given fraction, it has a terminating decimal expansion. So this is what converse of the theorem 1 states. I hope these two theorems are clear. Now we shall study another important theorem and we will solve some 2 or 3 examples on how to classify rational numbers as well as irrational numbers.